Let's begin with today's session. Hi, everybody. Welcome back to the KVA. We're going to be discussing something really exciting today, how to use the native multi-GPU solver in Ansys Fluent for accelerating your CFD simulations. This is a highly demanded topic. We get a lot of requests, a lot of questions from our current customers and prospects about leveraging this technology for gaining performance gains in their CFD simulation. So I thought I'll go ahead and do a KVA on this particular topic. So for today's agenda, we'll start with why look at GPUs versus CPUs, which is the more conventional way of parallelizing your CFD simulations. We'll talk about the existing GPU technology already present in the Ansys environment, which we basically refer to as using GPUs in the offload mode. We'll then talk about the native multi-GPU solver, which is fairly recent. It was introduced earlier this year in January. Talk about its present capabilities, discuss some performance benchmarks wherein we take example cases and see how the GPU computations fare against CPU computations. We'll talk about certain validation cases to compare the results between CPU simulations and GPU simulations. And lastly, we'll discuss the hardware requirements and licensing if you want to go ahead and leverage this technology. As always, if you have questions, comments, feel free to leave them in the Q&A box on your screens, and I will get to them towards the end of the KVA. Okay? All right. So why are we talking about GPUs? Anybody who's worked in the CFD field, anybody who's done CFD simulations knows that one of our biggest challenges is to reduce the computational time. And we employ various methodologies to achieve this, right? Sometimes we'll look at reducing our cell count, we'll look at simplifying the physics that we're adding to our simulation, or we'll go ahead and start investing in hardware resources so that we can get good performance gains, get high simulation throughput. Now, traditionally, conventionally, we've been using CPU cores for the parallelization, but as we can see over the past couple of years, there's been a lot of buzz around GPUs and what they can do in comparison to CPUs for getting this high simulation throughput. The reasons are, CFD should be used as a design tool, really. You want to understand the entire design space, evaluate multiple what-if scenarios. You don't want to be limited by the computational time or the hardware resources available to you to vary different parameters, different variables, right? So you want increased performances, but you also want to reduce your hardware costs and maybe even increase the ROI of your project by reducing power consumption. So that is where GPUs come into the picture. On the right, you can see some metrics that has been collected from nextplatform.com. Over the past couple of years, you can see how GPU performances compare to CPU performances, both in terms of peak memory bandwidth and peak double precision. GPUs almost give you 8 times the performance gains when compared to CPUs. And at the bottom here, you can see that if you forecast this trend over the next couple of years, then by 2025, you can hope to get almost 1,000 times increase in performance gains and solver ratings when you look at GPU computing as opposed to the conventional CPUs. So that is why we're talking about GPUs today. And just to make it clear, right, using GPU technology is nothing new. It has been around for a while, especially in the Ansys environment. Some of our flagship products like Fluent Mechanical, HFSS, and Maxwell have been using GPUs in the offload mode for a couple of years. I think in Fluent, it has been around since 2014. So when I say offload mode, what do I mean exactly? GPUs are very good in terms of bandwidth and parallelization, so they can increase your computational throughput. So what we traditionally do in the offload mode is we'll divide the overall simulation into CPUs and GPUs both wherein some isolated kernel of your simulation can be offloaded to the GPU while the rest of your computations are taking place on the CPU. What are some of the common applications that use this type of distribution? Anytime you're using, say, for example, the coupled solver, wherein you're doing linear algebra, matrix inversion, ray tracing, or maybe radiation models, then these isolated kernels can be offloaded to the GPUs while the rest of the calculations are taking place on the CPU. So you end up using a combination of CPUs and GPUs when you're using GPUs in the offload mode, okay? So on this slide over here, you can see two examples. This one is for an external aero problem, wherein we use the AMGX NVIDIA solver for offloading some of the linear algebra computations to the GPU, and then the rest was done on the CPU. You can see comparisons between using 32 CPU cores, and which are represented by the blue bars on this histogram. And then you can compare that to a combination of CPU plus GPU, when you end up using 28 CPU cores and 4 GPUs. So by using this approach of offloading a part of your simulation to the GPU, you can get around 4 times speed up for this particular problem. Similarly, there is another example where you are doing the discrete ordinates radiation problem. And again, this is mixed CPU GPU computing. For a 14 million cell case, we were able to get 3 times the speed up by using a combination of 28 CPU cores and 4 GPUs, right? And this is in comparison to doing the entire problem on 32 CPU cores. So you do get some good scale up 3 times here, 4 times here, if you use a combination of CPU and GPU cores. This is what we refer to as using GPUs in the offload mode. This is great if you're doing the kind of problem where the bulk of your computations can be isolated on your GPU. But the problem is you don't get significant advantages from this approach because a portion of your simulation computation is still taking place on your CPU. So your overall speed, your overall performance gain for your computation is somewhat throttled by the portion of the code that is not being performed on the GPU. So how do we solve this, right? How do we improve this performance even further? What we do is we do the entire simulation, every portion of the calculation on the GPU. And that is what we are going to primarily discuss in today's KVA, wherein we talk about the latest and greatest, the exciting new native or fully resident multi-GPU Fluent solver. In this particular approach, you're not using a combination of CPUs and GPUs, you're doing the entire calculation on your GPUs, okay? So, like I said earlier, this was introduced in January of 2022 in the Ansys Fluent 22 R1 release. And currently, this is still in the beta mode because it's being actively developed and tested. But these are some of the supported capabilities as of today. You can use both a single GPU or multiple GPUs, depending on the number of GPU cards you have on your machine. It supports all different mesh types, tetrahedral, hexahedral, polyhedral, polyhexcore, all types of Mosaic meshes that are supported by Fluent in the conventional sense. Both steady and transient simulations can be done. You can do incompressible simulations as well, and then subsonic compressible flows as well. Constant properties for materials or ideal gas properties are supported in the native multi-GPU solver. And a lot of the turbulence models are covered as well, including RANS models like standard, realizable K epsilon, generalized K omega, or even LES simulations and LES hybrid RANS simulations as well. Solid conduction and conjugate heat transfer are also supported in the current multi-GPU solver. So if you're doing, internal simulations, HVAC simulations, those type of problems are well supported by the native GPU solver. Moving walls and moving reference frames can also be done. You also have the ability to do non-conformal mesh interfaces and porous media zones in the GPU solver today. This GPU solver is supported both on the Windows and the Linux platforms. Given the physics that I just discussed, some of the target applications wherein this native multi-GPU solver can be used are low-speed external aerodynamics, internal flows, like I said, HVAC applications, and any type of conjugate heat transfer thermal management problem that you're doing today. Even though the GPU solver is in beta mode, I can tell you from personal experience that a lot of our customers have already started using it because their applications are similar to what you see on the slide, and they're seeing some great, speed ups and performance gains by switching from the CPU to the GPU mode of doing their calculations. Now, just to hone in on some of the 2022 R2 capabilities, this is the latest Ansys version that was released in July of this year. They've made some significant improvements to the user interface itself. Earlier, you had to launch it from the command prompt, but now you can launch it from the Fluent Launcher window itself. As you can see on the slide, all you need to do is check the native GPU solver box over here, and then select how many GPUs you want to solve on. And that will launch Fluent in the native GPU mode. And then depending on what type of models are available, you will see some options that are similar to the conventional Fluent GUI. The models that are not yet supported will be hidden. You won't be able to see them. As this application is being actively developed, we'll keep adding more and more options to the user interface depending on the physics that are supported in the future. In 2022 R2, you can do fully transient flows, including scale resolving simulations. So that is, again, a significant advantage. You also have some robustness improvements over the 2022 R1 version. Okay. All right. So we talked about the capabilities overview, but let's talk about the actual problem, right? How is the native GPU solver better than using the conventional CPU parallelization inside Ansys Fluent? So what I'm going to do is I'm going to go ahead and share some performance benchmarks so that you can see the metrics for what type of speed up can you expect. So this is an external aerodynamic problem where you're looking at the drag over a car. And we did this problem with 105 million cells on single precision with the generalized K-omega model. And to compare it to the conventional CPU approach, we are using the Intel Xeon Platinum Ice Lake cores as the basis for comparison. And then we compare it to a few other generations of CPUs. And then we also compare it to the A100 GPU card, and then keep adding the GPUs to see what type of scalability we can get. So as you can see, if you look at the Intel Xeon Platinum CPU core as the basis, then you can get almost 5 times the speed up by using a single GPU A100. And then as you keep adding the GPUs to the computation, by using 8 GPUs, you can get almost a 33 times increase in the speed up of this particular simulation. So if you're looking for equivalency, one A100 GPU card is roughly equal to 500 Intel Ice Lake cores, which is great, right? I mean, if you look at the parallel efficiency, it's almost 80% from 1 to 8 GPUs. So even in terms of scalability, it scales pretty well as you keep stacking on these GPUs. And even when you compare it to some more recent CPU generations, even in that comparison, the GPUs fare much better. So what this basically means that if you had a DGX, that DGX could replace almost 30 high-end dual CPU servers. If you look at this metric over here, because this is almost 33 times a single CPU core. Now, we're not just talking about simulation throughput, we can also talk about the advantages both in terms of power consumption and hardware cost reduction. So here on the slide, you see two graphs over here. When you're running simulations on multiple GPUs, you can have significant power consumption savings. For this particular problem, you could get around 4 times the power consumption reduction, which helps you improve the overall ROI of your project. And even in terms of hardware, right? For the same type of performance, investing in a CPU cluster could cost you 7 times more than investing in a GPU server for doing the same problem. So if you're looking at doing problems with a high cell count, and if you're looking to break the bank in investing in CPU cores, then going the GPU route could be a much better, much more feasible option for you. I've included a link to a YouTube video wherein we hear from the NVIDIA CEO. This was, I think, in 2021 last year, when he talks about how closely NVIDIA and Ansys are working together to actively develop this technology and get even better performance gains over the next couple of years. Ansys has early access to the technology that is being developed at NVIDIA. So we keep improving on these metrics. These are for the recent 2022 version, but I think in a very short amount of time, we can see that these numbers will improve even further depending on the technology that is being developed. Now, let's talk about another example over here. This is a poly Hexcore mesh with 2 million cells done with a single GPU. So we're not adding the number of GPUs to the computation, but we are trying to compare different GPUs in the commercial space and how do they stack up against a CPU simulation run. So you can see some of the common GPUs that support Fluent, that are supported and tested by the native GPU solver inside Fluent. And as you keep adding the number of CUDA cores, you can see that the speed up is that much higher. This is being compared to 48 CPU Skylake cores. And the Tesla A100 has the highest number of CUDA cores. So you can see the amount of speed up that you can get. It's almost 8 times the speed up you can get from 48 Skylake cores. This is another example wherein we did external aero simulation on a NASA CRM aircraft. This has around 5.9 million cells. This was a segregated solver run with double precision and generalized K-omega turbulence model. This one had ideal gas properties. Again, you can see that by using a single A100 GPU card, you were able to get almost 8.5 times the speed up from 32 CPU cores. And if you increased it from 1 to 2 GPU cores, then you're getting almost 12.6 times the speed up from 32 CPU cores. Now, this is a 25 million external aero problem with poly Hexcore Mosaic mesh. Keep in mind that this is 25 million, so that is a higher mesh count than the previous case. And here, if you look at the scalability, as you keep adding more CPU or GPU cores, you will see that the scalability is a bit better as you keep increasing the mesh count. So this is with a single CPU of 64 cores. You double it, you get almost 1-to-1 scale up. So with double the number of CPU cores, you get 2 times the speed. But then you add 2 GPUs and you get 8 times the speed. And if you end up adding 8 GPUs, you get almost 23 times the speed up compared to the 64-core CPU. Again, this is using the A100 GPU card, okay? And this slide I really like because it talks about the efficiency and the scalability and shows you the comparison between using GPUs for a smaller cell count and a higher cell count. So the application is just a generic combustor. So you have internal flow through this combustor. And from what I remember, this is again a poly-Hexcore mesh. And we did the comparison for the GPU solver usage on 2 different meshes. One is for 24 million cells and one is for 115 million cells. Now, there are certain terms on this graph that I'd like to explain so as to not confuse you. But basically what we're doing is we're plotting the MCI UPS and efficiency against the number of GPUs. MCI UPS stands for million cell iteration updates per second. So when we say that one GPU gives you around 20 MCI UPS, what that basically means is that for a 20 million cell count mesh, it is going to take 1 second to run one iteration. So as you keep adding more GPUs, you'll see these numbers increase. Basically, if you use 8 GPUs, then you should get you should be able to run one iteration within 1 second for 117 million cells instead of 20. So that's how these numbers scale up. Now, ideally, if your scalability was 100%, so then by adding 8 cores, you should have gotten 8 times the MCI UPS value, but you only get around 117.2 instead of roughly 160. So that is around 75% efficiency. That means that by adding 8 GPUs, you're getting around 75% scalability over here, which is what is represented by this blue line over here. Now, when you go from 24 million cells to 115 million cells, that scalability or that efficiency increases to 83%. So the more number of cells you have, the scalability will increase. I think this trend is also similar to using CPU cores in parallel. So by using that many GPU cores, you're getting very strong scaling, and you can leverage this to solve problems with a huge mesh count. This is another problem that we solved on the Ansys Azure cloud. This was for a 312 million mesh count. So that's like a huge mesh, right? And no wonder, they had to do this problem on the cloud because, you need a lot of CPU cores as well to solve this problem. So the baseline was using 4 CPU nodes, roughly a total of 176 cores. That gives you around 26 MCI UPS. What that basically means that you can solve 26 million mesh cell problem in which it takes 1 second for one iteration. Now, if you increase those 4 CPU nodes to 16 CPU nodes, that increases this 26 number to 103, right? So that's almost 99% parallel efficiency, which is great. But what happens when you swap out these CPU nodes with GPUs? So by using 10 A100 GPUs, you'll get 414 MCI UPS. I mean, that is impressive, right? That is almost equivalent to 2,830 CPU cores. And this entire problem, a 312 million mesh, that converges in about 15 minutes. So that's huge. And if you're looking at just cost saving, right? I mean, this was done on Ansys Cloud, so it's very easy to measure the cost saving that you'd be able to get by switching from CPUs to GPUs. You're able to save almost 5.2 times the cost by using GPUs. So that's, again, pretty impressive. And one of the main objectives in switching to the native GPU solver as opposed to using parallel CPU cores. Now, the same problem when it is scaled up even further, instead of using 10 GPU cards, if you end up using 24, then you get a parallel efficiency of almost 81%, which is roughly equivalent to 5,500 CPU cores. So again, that's great. And you see this level of parallel efficiency because it's a huge mesh, right? It's a 312 million mesh. Okay. So this is really good. And let's see a problem example for conjugate heat transfer. Till now, we've been talking about external aerodynamics. So this was a generic permanent magnet E-motor. We had different cell zones. Some of them were fluid zones, 3 internal fluid zones, and then 13 remaining solid zones. Some of the solid zones had heat sources supplied to them. And then you also had convective outer walls. And this was done in a segregated solver with SSD K omega, and it also had moving reference frame enabled. So almost all of the physics that you have available with the native GPU solver, all those physics were added to this particular problem. So again, if you compare the solve time between doing this problem on CPUs and GPUs, you can get almost 10 times the speed up. So if you look at the solver rating, if you look at the equivalent solver rating, a single A100 GPU card ends up being comparable to 220 CPU cores. So imagine investing in, 220 CPU cores, and then imagine investing in just an A100 GPU card. So definitely there's a lot of advantage in using the native GPU solver instead of going the traditional route. All right, so till now we've talked about the performance benchmarks wherein we compare how GPUs fare against CPUs in terms of speed up and scalability. But what about accuracy? You don't want to compromise on accuracy. You want to get the same result from a GPU run simulation as you'd want from a CPU run simulation. So let's see how the GPU results compare to CPU results. So this is a very standard benchmark case in the CFD community. It's an asymmetric diffuser, nothing fancy, just internal flow with a hexahedral mesh. And what we are basically doing is comparing the CPU and the GPU results. This mesh had around 7,000 cells, turbulent flow with separation and reattachment. And you're basically setting this up with the generalized K omega model, and the pressure velocity coupling is done using a segregated solver, second order upwind for both pressure and momentum, and also turbulence. So this plot over here shows you the comparison between GPU and CPU results. As you can see that they overlap each other, and you're getting the same results from the GPU as you are getting from the CPU. So no lack of accuracy here for this particular example case. Similarly, this is again a very popular benchmarking case, the backward facing step with a heated wall. It again has a hexahedral mesh. There's a velocity inlet, and there's a heated wall here at the bottom where you're applying some amount of heat. What we did was we ran this case with both the CPU conventional method and then ran it on the native GPU solver. We are looking at the velocity profiles at different sections along the axial length of this backward facing step. And as you can see from the legend, both the GPU and the CPU runs give you similar results. They're overlapping, so you're not even able to differentiate between them. So pretty comparable. And the CPU results are already well validated against literature results, as I'm sure a lot of the CFD users already know. So that means that the GPU results are also validated against literature data. Now, this is a slightly more complicated problem. We have a flame holder simulation, and we have a velocity inlet passes through a triangular section over here, and then we have a pressure outlet over here. You can look at the internal section over here. The reason why this is a little bit more complicated than the previous two validation cases is because we are using a fully LES mode of solving for the turbulence over here. We are using a simplex scheme for doing this simulation. We started with the steady state case, and then it switches to a transient case after we get to a reasonable solution. Some other settings are mentioned here on the slide. You can see that this is a fully transient problem, and you're adding a lot more physics than the last two cases. But when we compare the CPU and GPU results, both in terms of variable contours and also data at specific actual locations, they match up pretty well. The upper contour is for the CPU-derived result. The lower contour is for the GPU simulation. These look pretty identical, both for the instantaneous velocity and mean velocity. And here you're looking at the mean velocity and also comparing it with the experiment. The CPU and GPU results look fairly comparable. They deviate a slight bit from the experimental results. But if you're just comparing GPU and CPU results, they're fairly consistent, even at different X velocity profiles at different locations. You can see that they overlap each other. So in terms of comparing the results from your CPU run simulations and GPU run simulations, I think we can conclude that for the physics that you can solve on GPU solvers today, you should get pretty much the same results as you would from your conventional CPU run. Now, we talked a lot about the capabilities. We talked a lot about the performance gains. We talked about accuracy. But what type of hardware do you need to have for leveraging this GPU solver? And then how does that pair with the high-performance computing licensing from Ansys? So currently, and I use the word currently because this is for the 2022 version. This is subject to change as there are more developments in this field or the licensing architecture changes with future releases. But currently, the Fluent GPU solver is available with the CFD Enterprise license. I think in a previous KVA, we talked about the different packages available inside Ansys CFD. So currently the GPU solver is only available with the enterprise package. And the enterprise license, it accounts for all different physics. It gives you access to all multi-physics bundles. So from a CFD standpoint. So the GPU solver is available with the CFD enterprise package. And the way the licensing works is it is based on streaming multiprocessors, okay? Not the number of GPUs that you have, but the number of total streaming multiprocessors available on those GPU cards. I'll talk a little bit more about this in the next slide so that it's a little bit more clear. But what you basically need to remember is that right out the box with CFD Enterprise, 40 streaming multiprocessors are already included. That means that up to 40 streaming multiprocessors, you will not need any additional HPC licensing. As long as you have CFD Enterprise, those 40 SMs are already included. You can use up to 40 SMs for doing your simulations, no additional HPC licensing needed. If your GPUs have more than 40 SMs, more than 40 streaming multiprocessors, then you would need to have additional HPC licensing, wherein for each additional streaming multiprocessor, you'd need one HPC task. These are very compatible with the existing HPC licensing inside Ansys. So if you already have HPC packs or HPC work groups, then all you need to know is how many streaming multiprocessors do my GPUs have in total? And you would be able to leverage your existing HPC to work with them. You don't need anything extra. They're highly compatible with the HPC licensing architecture in Ansys as of today. So what are these streaming multiprocessors, right? Perhaps a lot of people may not be very familiar with this concept. So let me go ahead and explain a little bit about it. GPU cards, they're made up of many streaming multiprocessors, right? And each of these streaming multiprocessors in turn contain many CUDA cores. I talked about CUDA a little bit earlier, I think in the initial slides, but basically CUDA stands for Compute Unified Device Architecture. It's basically the parallel computing platform, an API that is available, say for example, an NVIDIA GPU card. So each GPU card has some streaming multiprocessors, and then those streaming multiprocessors in turn have CUDA cores, okay? If your GPU card has less than or equal to 40 streaming multiprocessors, then you don't need additional HPC licensing. If your GPU cards have more than 40 streaming multiprocessors, then you would need more HPC licensing depending on the additional number of SMs on your GPUs. So say, for example, on the right over here, you see some commercial GPU cards. These, you might be familiar with these names. You can see how many SMs each of them have and how many CUDAs they have individually. So the Tesla A100 that we've talked about in a lot of examples, that has around 108 streaming multiprocessors, and in total, 6,912 CUDA cores, making it one of the most powerful GPU cards that can be used for high-intensity, computationally demanding CFD simulations. Okay, so if we are talking about the kind of GPU that you may have or that you may want to invest in, you would want to look at the type of problem that you're trying to solve. So this table highlights some common GPUs that are available in the commercial space today. And these range from being installed on, standard laptops to high-end workstations or, being a next-gen server GPU. Okay, so if you look at a standard laptop or a desktop GPU, roughly, they have around 20 to 30 streaming multiprocessors, as you can see in this column over here. And because these are less than 40 in number, you will notice that you don't need any additional HPCs for just using these to do your CFD simulations. So if you have any one of these, and there are less than 40 streaming multiprocessors on these cards, then you're good to go. Just a CFD enterprise license is all you'll need to, run your CFD simulations. And these are typically the kind of problems that you'd run depending on the RAM available on these GPU cores. So you can see over here what these rows signify. Now, for example, if you're going to a Tesla P100 or an RTX 6000, these now start having more than 40 streaming multiprocessors, and that would mean that you'd need additional HPC licensing. Now, whether or not you need something this high end, again, depends on your problem. You may not want to invest in something that is overkill for the type of CFD simulation you're trying to solve. If you have something that is, roughly 10 million cells, maybe you can get away with a Quadro P6000 and then just use your CFD enterprise licensing without purchasing additional HPC. If you are looking to build a CPU cluster and instead would like to invest in a GPU server because that's going to save you a lot of cost, then maybe you want to get something like the Tesla A100 or H100, which can solve bigger cell counts. And then, additionally, you will require some HPC packs for doing these type of computations. Okay. So hopefully this table is a good guideline for understanding what type of GPU technology you already have or may want to invest in. If you need more information about building the right workstation for the type of CFD that you are doing, feel free to reach out to us. We can give you some more information. We can also tell you how to check how many streaming processors you have on your machine, or if you should leverage either one or more than a single GPU for doing your simulations. So we can provide you some more information if you need any guidance in that particular department. All right. So to summarize, I just want to reiterate the things that we learned today. The native multi-GPU solver in Ansys Fluent is going to be able to give you significant performance gains over the traditional CPU-based approach, or even the GPU offloading-based approach, because a single GPU can offer the same performance as more than 400 CPUs. If you go back to some of the slides that I covered in the performance benchmarking examples, you'd be able to see that equivalency. And because the multi-GPU solver allows you to leverage more than a single GPU, you can add even additional computing power to your CFD simulations to get higher simulation throughput. We also looked at some validation cases and realized that if you compare CPU simulation results and GPU simulation results, they're quite comparable. So you're not really compromising on accuracy when you choose the native multi-GPU solver inside Fluent. And by investing in GPU servers, you would be able to save on hardware costs and also power consumption costs, thereby increasing the ROI of your projects. As far as the licensing goes, the native Fluent GPU solver is available with CFD Enterprise. It runs out the box without HPC licenses, provided your GPU card has up to 40 streaming multiprocessors. Anything more than 40 streaming multiprocessors would require additional HPC license. And lastly, this is compatible with the existing Ansys HPC licensing architecture. So if you already own HPC packs or HPC workgroups, then you don't need to worry about getting anything extra. You can just start using the GPU solver on your machine today, and you should be good to go. If you have any other questions about GPU compatibility or whether or not your application is supported by the GPU solver today, feel free to reach out. We'd be happy to help you and share some resources or guidance with you. If you guys already have Ansys Fluent on your machines, you might want to just launch the GPU solver in the beta mode and try to do an internal flow or a conjugate heat transfer problem. See what type of speed up you're gaining by switching to the GPU solver. I'm sure you guys already have GPU cards on your machines, so you can always see if you're getting any advantage from switching to the GPU solver and see how the UI is different from the conventional CPU-based method. It's not very different. It's just a matter of which models are available in the current particular release. And in January, we are going to have another release, 2023 R1. So stay tuned for that. I'm sure there'll be a lot more interesting capabilities added, both to the GPU solver and then also to Fluent in general. So we'll definitely have some sessions regarding that. All right, so I don't see any questions in the Q&A box. But like Christina mentioned earlier, feel free to share your feedback with us. And if you have additional questions, you can always reach out to support@ketiv.com. And we'd be happy to check back with you. All right. So with that, let me go ahead and end today's session. You guys have a good one, and we'll meet soon in the next KVA. Thank you. Bye-bye.